Whether you've just started teaching or spent decades in the classroom, you know there's always more to learn. But where do you start? Well, here at Hillsdale College, we have the answer for you. Tried and True, a primer on sound pedagogy by Hillsdale College professor Daniel Copeland. In this little book, you'll read lessons from more than 25 years of Dr. Copeland's classroom experience. It's all distilled into 14 easy-to-read chapters on lesson planning, assignments, and classroom management, and it will help you improve your skills and inspire you as a teacher, one of our most important professions. Whether you've been in front of the classroom for years, or this is your first year, when you read Tried and True, you'll find something to help you keep improving every single day. You don't need to go at it alone. Let Dr. Copeland's real-world experience encourage you and inspire you. You can get your copy today at hillsdale.edu/true. That's hillsdale.edu/TRUE. Thanks for listening.
Welcome to the Hillsdale College K-12 Classical Education Podcast, bringing you insight into classical education and its unique emphasis on human virtue and moral character, responsible citizenship, content-rich curricula, and teacher-led classrooms. Now your host, Scot Bertram.
Thanks for listening. The Hillsdale College K-12 Classical Education Podcast is part of the Hillsdale College Podcast Network. More episodes at podcast.hillsdale.edu or wherever you find your audio. You also can find more information on topics and ideas discussed on this show at our website, k12.hillsdale.edu. We continue a series of episodes from presentations delivered at the Hoogland Center for Teacher Excellence seminar on the art of teaching the sciences. The Hoogland Center for Teacher Excellence is an outreach of the Hillsdale College K-12 Education Office, offering seminars in classical academics and pedagogy for teachers nationwide of any background. Seminars are led by the faculty, leadership, and master teachers of Hillsdale College. There is no cost to attend, and attendees may earn professional development credits. To learn more, visit the webpage for the Hoogland Center for Teacher Excellence at k12.hillsdale.edu. Click the Events tab and look for Hoogland Center, or write to cte@hillsdale.edu. In March of 2024, Dr. Matthew Young, Dean of Natural Sciences and Professor of Chemistry at Hillsdale College, spoke to a gathering of teachers and school leaders in an address titled The Great Principles of Chemistry.
Okay, good morning, everyone. It's a privilege to be here. I hope you're enjoying the presentations thus far as much as I am. The first, I didn't get a chance to hear Mrs. Theory's, but I know from hearing her speak before that it was excellent, and the other two that I attended, I really enjoyed. So, Great Principles of Chemistry. As Eric just said, this is the title of the Hillsdale online course that I recorded last year and is available for free online. But maybe more importantly in my mind, and what I want to focus on today, it's also the title of a course that we offer at Hillsdale College, The Great Principles of Chemistry. 3-credit course, a full semester of chemistry. And every student that comes through Hillsdale takes chemistry as part of their coursework. And so this course is part of our core curriculum. And so I want to talk a little bit about what this course is and some of the unique features that it has. And I hope that the idea here isn't that you would go and copy this in your own classrooms, but just a chance for us to think about chemistry. I think sometimes when we think about the natural sciences, in certain contexts, we especially historical contexts, scientific revolution, we gravitate towards thinking about physics. And then sometimes when we think about what are children interested in, let's look around at nature. We might gravitate towards biology. And I think sometimes chemistry gets lost in this conversation about the natural sciences in K-12 education. And so I hope that what we talk about today might help us to broaden our thinking about chemistry and hopefully capture your interest about chemistry. And so this course is, as I said, every student takes it. It's part of the core curriculum. call it the Great Principles of Chemistry. And so the course is organized around these 7 ideas, which we call the Great Principles. And I want to think about these for a few minutes. So the first one is that chemistry gives us an important contribution to our pursuit of what is true and what is beautiful, central to a liberal arts approach to education. And then when we think about what is the contribution of chemistry, this is almost true. All matter throughout the universe comes from only about 100 unique elements. And it's electrons in atoms that are responsible for bonds holding the elements together and creating the tremendous variety of different kinds of materials that we observe in the world. The structure of a molecule dictates its properties. Chemical changes occur through just a few types of reactions. And most reactions here on Earth take place in the presence of water. And then finally, the processes of life are driven by molecules. So you can see we go from this very basic, like what are the elements, what are bonds, all the way up to the life processes and what is the chemical basis for processes of life. And so I think when we look at this, one thing that really maybe should strike us is that we can look at some very kind of slender list of principles and almost simple principles. And out of these things can come great complexity. I think one thing that I always hope will really strike students of chemistry is that when you look around yourself, there are so many different types of matter, so many different examples of matter, distinct compounds. But on the other hand, they're all built up from not that many different elements. And so you have this kind of simplicity giving rise to a great degree of complexity. And then we also see a kind of a movement here from very fundamental things all the way up to living systems. Chemists have a nickname that they use for chemistry. They call it the central science. So we could think about what is trying to be conveyed here by calling chemistry the central science. Maybe one thing would be an idea that chemistry is centrally important, or kind of, it's the central science is really important. But I think also it could be central in the sense that chemistry has connections with many other areas of natural science and then also applications of natural science. Think of materials science, medicine. We could think about agriculture or geology. All of these things, chemistry has some connection with them. And in fact, if you go to a large university, sometimes the course with some of the very biggest enrollments across the whole campus will be general chemistry. Why? Not because there's a tremendous number of chemistry majors at the university, but because if you want to study any number of areas, then general chemistry is something you're going to have to take because it has this connection to all kinds of sciences that leverage the properties of matter. But I think my favorite way of thinking about chemistry as the central science is thinking about chemistry as providing a bridge between physics with its very fundamental theories about motion and energy and forces, distilled in many cases into mathematical formula like we talked about like was covered last night. Providing a bridge between that and biology with all of its complexity of studying living organisms and populations of organisms. Chemistry exists in that space between those two things, I think, in some ways, looking at the level of molecules. And so we kind of see that bridge here as we kind of think about what are the elements, what are electrons? That's kind of on the physics side of things. And then as we build up to the molecules that are responsible for life, we're moving into the interface of biology. And so chemistry is the central science at this molecular level. One of my favorite definitions of chemistry, coming from a textbook that I've used, says that chemistry is the science that investigates the molecular reasons for macroscopic processes, or the processes occurring in our macroscopic world. So we live at a certain size, and we manipulate matter with tools or with our hands or whatever. But chemistry gives us insight into the molecular reasons for what we see in the world. And so there's this molecular scale. And I think one of the things that's fascinating about chemistry, but also frustrating sometimes for students, is that we're always going back and forth between the world at our scale and macroscopic quantities of matter, and then also at the molecular scale, and thinking about the properties of atoms and molecules. But we haven't seen those things, and so it's a very abstract representation, but chemistry is largely about this molecular scale. Okay, so the central science. Let me tell you a little bit about the way the course is organized. So this is a course where we meet 3 times a week for 50 minutes, like lots of college courses. And first, let me talk a little bit about the goal of the course. So this course is the great principles of chemistry. It's not a prerequisite for anything. Okay? It's not a course that is preparing you to move on in your study of chemistry. It's a course that any student takes, no matter what their major is. And so it's not a prerequisite for anything except a kind of comprehensive education. And so this allows for us to kind of relax a little bit, thinking about the content that must be covered in order to move on to another chemistry course. For many students who take this course, it will be the last time that they formally study chemistry in their lives, probably. And so we can think about, and so the goal of the course is to give students a picture, not to develop a comprehensive set of skills that chemists need, but to give students a picture of what chemistry is and the way in which chemistry can contribute to human understanding of the world. And so, like I said, we meet 3 times a week. Two of those meetings are basically lectures where we talk about important concepts from chemistry. The third day, though, is different. The third day, every other week, we have a lab where the students go into lab and do a hands-on experimental lab. And then every other week on that third day, we have a discussion where the students have read something and we get together and we talk about it in a way that might be reminiscent of what people would think, the activities you would think of as going on in a humanities course. And so it's really those discussions that I want to focus on. But think about what in those kind of 3 activities, lectures, labs, discussions, the students are getting. They're getting exposure to and exploration of some of the important concepts of chemistry. This is going to be important in any chemistry course. They're getting hands-on experience doing experiments themselves. Chemistry is very experimental science. And so as part of a course, there has to be some kinds of hands-on manipulation of matter, taking measurements, things like that. But they're also getting some larger context. How does chemistry connect to some other ideas? What is the historical way that important ideas in chemistry have been developed? I think that context is very enriching for students of a variety of majors in this course. And so it's that's what I want to focus on. What I want to focus on is what I'm calling some liberal arts connections within a chemistry course. That can connect us to ideas that are bigger than chemistry, that are important across the disciplines in the liberal arts. And so the first idea that I want to talk about is the idea of truth. And we've heard a lot about this in the talk last night, in Dr. Diener's talk just in the last hour, thinking about the idea of seeking truth. And so when we think about the liberal arts, what is the goal of liberal arts education? Some of the things that we've been hearing about are the idea of giving a person the tools they need to be able to stand before reality and see it, what is there, apprehend reality in a comprehensive kind of way. as best we can in our limited capacity to do so as humans. So can we see this kind of whole, Dr. Diener talked a lot about the whole picture of the different disciplines looking at what is real. And we talked about what is, and also last night's talk touched a lot on this too, making contact with reality. We've heard about seeking knowledge for its own sake, wanting to know things, coming from the tradition, coming all the way from Aristotle. Aristotle said, to be learning is the greatest of pleasures. So seeking knowledge just for its own sake. And then we've also talked about developing the faculties of the human mind. The liberal arts are these disciplines that can hone the ability to think, develop our mental faculties. And so when we think about chemistry then, oftentimes the students think of chemistry as being a very practical discipline. And why do they think this? Because chemistry is a very practical discipline. It's very useful. And actually it results in all kinds of technological advancements. And this is why 70% of the people who earn PhDs in chemistry go into industrial positions. This is not true of philosophy or history, but it is true of chemistry. And this can create a tension, I think, sometimes, because with this very useful discipline, students wonder, why am I taking chemistry? I'm not going to go into pharmaceutical industry or any number of industries which leverage understanding of chemistry. And so I think it's important to tie chemistry to these larger goals of the liberal arts. Even such a practical discipline as chemistry enables us to see physical reality at the molecular level and further understand the world that we live in. And that's really the focus for us in the context of liberal arts education. And then it becomes very useful, of course. There's lots of things you can do with that understanding, but those always come after seeking an understanding about the way things are. And so, chemistry has an important contribution to finding out what's true. Now, there's another aspect of this that I like to bring up with the students, which is who gets to undertake the project of liberal art education? Like, who has time to contemplate what is true? Well, in the past, it's been a very few that have had that kind of privilege, right? Because the bottom line is there is a lot of work to be done. There's a lot of work to be done just to survive. But what chemistry and the other natural sciences have done is they've contributed to the project of liberal education in a kind of a roundabout way that we often don't think about. And that is the technologies that have enabled our modern way of life have had a democratizing effect where many people now are not just stuck with the drudgery of labor in order to try to survive, but actually we have time. We have free time. What people call leisure. We have leisure. And then the question is, what do we do with it? But it gives, maybe not anyone, but many people an opportunity to devote time to the serious cultivation of the mind, thanks in part to chemistry and the way in which it has enabled a modern way of life where we have space to do this. Now, it's also enabled us to just watch Netflix and things like this. So we could use that time in various ways, but it can be possible to use it for cultivating one's mind. And so it's not just for the privileged few anymore, thanks in part to chemistry. So I think there's two ways in which chemistry contributes to the liberal arts. Okay, connection number 2 is beauty. I like to think with the students about is there any connection between chemistry, and oftentimes, the people in this room that teach high school chemistry know that it's a significant challenge, and students will often come into a chemistry course with a certain amount of intimidation. They think, it's going to be hard for me to understand this. The material is quite abstract, some fear about the mathematics associated with it. Talking about beauty maybe can help ease some of those fears. And often students won't immediately think chemistry is connected in any way to beauty. But how could chemistry be connected to beauty? Well, I think one way is we can look at chemical artifacts. Again, this could be all the way from the molecular up to the macro scale. But what are some aspects of artifacts that we could associate with beauty? Well, I think one obvious one is symmetry. Humans have had an interest in symmetry since ancient times. And it's very interesting to look at various molecules and pick out their symmetrical elements. Some molecules are quite symmetrical. And so I think they can be beautiful in that way. Although it's interesting when we talk about what do we mean when we think a certain molecule is beautiful. I mean, we don't look at a molecule. For most of history, it's been totally impossible to see a molecule. No one's ever seen a molecule. Now, we have some scanning probe microscopies that can give us images of molecules, but for the most part, we don't look at molecules. We look at some kinds of abstract representations of molecules, right? And so I think it's interesting to think about those representations and how they do and don't correspond to reality. But nonetheless, those representations, I think, can be beautiful. But it's not just symmetry. We could also think about complexity. Like if you think about maybe a representation of a protein, macromolecule, then you might think, okay, it's not so much the simplicity and the symmetry of that representation, but it's the complexity of that structure. And not only the complexity, but maybe also the function. I think the function that molecules have could somehow contribute to the beauty, your idea of beauty in the molecule. Oh yeah, and then we also shouldn't forget color. So on the macro scale, think about the artist's palette. Well, the artist's palette has been influenced in really important ways by chemistry. How new and more stable pigments. And when the painter makes a painting, how's that painting going to hold up to exposure to air, exposure to light, things like this? Well, the chemist can help with that, right? So I think there's really interesting connections between art and beauty because art uses materials to make beautiful things. Then those materials come in large part from chemistry. But it's not just artifacts. I also want to think about experiments. What makes a beautiful experiment? There's been some articles and books written about the most beautiful experiments. And actually, I think there's a book called The 10 Most Beautiful Experiments in Science, or something like this. And what's interesting about that book started out as a survey about the most beautiful experiments in physics. And so that book, all of the experiments are physics experiments that uncovered something about the natural world. And I think it's interesting to think about the experimental nature of chemistry and what does a chemistry experiment look like. And I want to come back to this a little bit later. What does a chemistry experiment look like? So some things, well, let me just point out for now, oftentimes a chemistry experiment can have a kind of a creative or artificial character to it because in many cases the chemist is trying to create something. This is very different than a physics experiment where the scientist is observing what nature is like. But people have put forth the qualities like invention, elegance, perseverance, imagination, ingenuity, simplicity as hallmarks of beautiful experiments. But I want to show you an example of an experiment that's very different in character from something like Millikan's oil drop experiment, elegantly determining fundamental charge of an electron. This is like one experiment gets this great and important data out of it. What this structure on the left here is vitamin B12. In 1960, Robert Woodward and a collaborator of his, so he was at Harvard, his collaborator was at ETH Zurich. They embarked on an experiment. And this experiment was, can we take this molecule? So vitamin B12, the molecule on the right there of the screen is what they wanted to try to make. And in 1960, it was understood how to convert that molecule into vitamin B12. Not easy, but it was understood how to do it. And so they started on an experiment. And the experiment was, can we create from scratch, can we make from scratch, it's called a total synthesis, this molecule that's on the right here. Lots of atoms there. And you can see some nice symmetry there. So in 1960, they embark on this experimental project. Can we make this molecule? And about 100 people were involved in the project over just over 12 years. So the people are mostly postdocs rotating through these two labs. This is a tremendous experimental undertaking. And eventually, the synthesis was successful. Lots and lots of steps, but they're able to build this molecule. Think about the power of being able to do that. The chemist can take just the building blocks, the elements on the periodic table, and build this complex molecule. And it's a natural product. It's something that occurs naturally, which is another thing I think that's really interesting to think about. Nature is really, really good at chemistry. It can make amazing molecules that are really hard for the chemist to make from scratch, but this is just a sort of a brute force of human ingenuity. So what is the beauty here? I think the beauty here is almost like the beauty of it's a beauty of strategy, perseverance. It's like the beauty of a chess game, well played. Being able to see all these moves, all these steps to make this kind of molecule. And so the point here is that this is a very different activity than Millikan trying to determine the charge of an electron in an experiment. And so I think it broadens our view. I think chemistry broadens our view of science. What is an experiment? What does scientific activity look like? In some ways, this is not really hypothesis testing. This is a goal, a project, trying to create something from just the elemental building blocks. Another example, I think, of beauty is the icon of the discipline, the periodic table, right? Where we've got very kind of neat arrangement of all of the elements, all the elements in the whole universe. We haven't seen most of the universe, but we know that there are no other elements other than these. And so, we've got our 18 columns, if we ignore the intertransition metals at the bottom there. 7 rows, totally filled in. Everything's filled in sequentially. Actually, this has only been completely filled in up to element 118 since about 2010. And so we actually live right now, from chemistry perspective, in a really interesting time where we did it. People synthesized these elements all the way up to 118. So I have the students kind of speculate, what do you think we'll be able to make 119, 120? Where would it go on this table? There's no more open spaces. So I think that's kind of interesting to think about. But the beauty of the periodic table. Now, in terms of being sort of a beautiful summary or display of the order of the physical universe. Now, one thing that I think is interesting to think about is, does scientific analysis in any way detract from beauty? Like when we analyze things, does it detract from our sense of beauty? Think about, you could think about a flower, you could think about the night sky, you could think about leaves in the fall, things like that. A sunset, or even the different pigments within used in a painting, something like that. Does it detract? I think sometimes there's this idea that science, with its mechanistic explanations, can kind of distract us from the beautiful. But I would like to propose that understanding of really what's going on at the molecular level is a deepening of our sense of beauty. It can deepen our sense of beauty. Dr. Diener talked about people looking up at the night sky, and one thing that I always think about is, ever since ancient people, right? I mean, that's one common experience all humans have had, is looking up at the night sky. But actually, most people haven't really known what they're looking at, right? It's very hard to tell what you're looking at. How far away are these twinkling lights? Well, what science tells us is that the universe is much larger than anyone could have possibly imagined, right? And so this is I think can really enrich our sense of the beauty of the universe rather than detract from it. I think it's similar with chemistry. Being able to look inside matter and see what's going on can enhance our sense of beauty. Okay, I got to speed up here. So, truth, beauty. Connection number 3, history. Putting some scientific information into historical context. Any number of fascinating stories, of course, in the history of science. So, for example, when we talk about the discovery of oxygen and the theory of combustion involving Antoine Lavoisier, often thought of as the father of modern chemistry, and Joseph Priestley. But also involving, in some ways, Benjamin Franklin. Benjamin Franklin was close friends with both Lavoisier and Priestley. And so I think I'm going to kind of skip over this story. Probably a lot of you know this story of these two guys working mostly independently, although they did get ideas. Lavoisier got a really important idea from Priestley to discover oxygen and its role in combustion reactions, and move from this, maybe we could call it a paradigm of the phlogiston theory, to a paradigm of oxygen's role in combustion. But it's a fascinating story. But what I want to focus on for a historical connection is when we go through different laws in chemistry. So I want to point out two. In the late 1700s, Lavoisier himself is doing these very meticulous measurements of mass. And he's able to show for a variety of reactions that if you account for all of the mass before and after the reaction, it's always the case that there's no change in the mass, right? The mass is conserved. So this is just something that we observe, and so we call it the law of conservation of matter, or the law of conservation of mass. It's the way things are, right? And there's another law developed around the same time, late 1700s, articulated most famously by Joseph Proust, called the law of definite proportions, or the law of constant composition. And this says that if you take a sample of a compound, it's always the case that that compound consists of its constituent elements in fixed proportions by mass. People thought maybe substances like water, for example, maybe not so much water because it was thought of as an element, but if water is a compound, then maybe water is a variable mixture of hydrogen and oxygen. And what Proust showed is no, it doesn't matter. Any sample you take, it will have fixed proportions by mass of hydrogen and oxygen. So this is the law of definite proportions. Well, okay, but these are just laws. So as the ideas develop in time then, how can we explain? Why is mass conserved? Why do we see these definite proportions by mass of any compound? Well, right at the beginning of the 1800s, John Dalton proposes his atomic theory, right? And we can trace this idea of the atom all the way back to ancient Greek philosophy, Democritus, for example, speculating that, yes, maybe there are indivisible things. But what Dalton says matter consists of indivisible particles called atoms. The atoms of a given element are going to be identical in any relevant way. Maybe they have the same mass, same size, same shape, things like this. When atoms come together to form compounds, the atoms combine in definite proportions to form molecules. When you have chemical reactions, what's happening? It's just these atoms rearranging. You could imagine, like, if you had a pile of Lego pieces. There's lots of things you could build with them, but you're just building them out of those same pieces. So obviously the mass isn't going to change depending on how you arrange them. So something similar here. Reactions are just the rearrangement of atoms. And so we can see then that this proposal, this atomic theory, explains these empirical laws based on mass measurements of macroscopic samples. And so we can see this connection of the ideas in the way that they've developed historically. Okay, the fourth connection is humanity. Dr. Diener talked about the humane nature of science, science being intimately connected with the kinds of concerns that humans have, the kinds of concerns that make us human. The example that I want to use is we look at the life and times of Gilbert Lewis. So this is a science conference. How many of you have heard of Lewis structures? Good, yeah. I think hopefully pretty close to 100%. So Lewis structures, right? A way of depicting molecules that shows the sharing of electrons between atoms to form what we call covalent bonds. So Gilbert Lewis is the person that is, the namesake for Lewis structures. So Lewis is a man who comes to University of California at Berkeley in the early 1900s, or early part of the 20th century. And it's a small chemistry department at that time. He sets up shop there and is hired as the head of the chemistry department. So he forms a chemistry department at Berkeley. Brings along a couple people that he already knew from MIT, and he runs a few people off that were already at Berkeley. And then he starts to build a department. And he actually builds a department that's quite insulated. He only hires people for many years, decades. He only hires people at Berkeley that he already knows, mostly graduates from Berkeley. And so he builds this faculty, and in 1916, he publishes a paper called The Atom and the Molecule that describes the idea of the covalent bond. Then Lewis goes off to serve in World War I. So he publishes this paper, but he's in this very insulated department. He doesn't attend scientific conferences, and also he leaves to go to war. Meanwhile, a scientist named Irving Langmuir reads Lewis's paper and starts to really become impressed by these ideas of the shared pair of electrons. And Langmuir chews on this stuff, and then he starts to present it. He goes to scientific conferences. He's a outgoing person. He's a good speaker. He coins the term octet rule. He coins the term covalent bond. And he starts to get the word out about this new theory of how nonmetal atoms bond together to form molecules. And so it becomes known as the Lewis-Langmuir theory. Lewis comes back to the United States and is extremely annoyed to find that these ideas are associated with Langmuir. And so there's lots of interesting correspondence you can read where Lewis is clearly annoyed by this situation. So basically Lewis has this rivalry with Langmuir. And he's concerned about Langmuir being credited with ideas that were his. On the other hand, Langmuir's been the one that's been out talking to scientists and participating in the scientific community and exchange of ideas. And so it opens up, I think one thing it does is it humanizes science. Like, scientists are not some kind of special class of people that don't have emotions or something like this. Right? Scientists are regular, curious people, and they are humans just like anyone else. And so you have these different things that happen to scientists. You've got these rivalries and these concerns about credit and things like that. So we talk about interpersonal dynamics, and so should that play any role in something as kind of supposedly as objective as science? Well, scientists are human. And so interpersonal dynamics are part of the story of the development of science. We talk about the importance of credit. Is it important to accurately assign credit for ideas? And sometimes students will at first think, it doesn't matter, right? It's all about what is true, getting a better grasp on physical reality. It doesn't matter who discovered it, but then they realize, well, it might lead, first of all, that seems to violate a sense of justice, and it might lead to a kind of an intellectual anarchy where anyone could just say, like, well, I came up. Our students write papers and they say, well, I just came up with these ideas, when they didn't. And then we call that plagiarism, and they get kicked out. So it is important, right? But on the other hand, this thing of chasing credit, we talk about prizes. Lewis was, one of the things that really irked Lewis was he was nominated for the Nobel Prize, I think, 35 times. He never won a Nobel Prize. Langmuir did win a Nobel Prize, not for this covalent bond stuff. He did some other important work on his own merit, but he was a Nobel Prize winner. This made Lewis furious. And then the close of the story is Lewis is 70 years old. On a Saturday, he's in his lab at Berkeley doing some experiments by himself. And he dies at his lab bench, and it's unclear whether it was a suicide or an accident. So there's lots of intrigue here, and Lewis has a difficult personality, and so he's a little bit hard to get along with. He doesn't like people that he doesn't already know. He doesn't attend conferences. Langmuir is this gregarious guy, and so we talk about, like, even just the role of personality. Should that play in? What does that have to do with science? Responsibility of a scientist to publicize their work or share their ideas with the scientific community and with the public. Most science, of course, is funded publicly, and so what responsibility do scientists have to share what they're up to with the public? So anyway, the point is, this story, everybody knows about Lewis structures, but this backstory of who Lewis is and these various aspects of it, I think can be really interesting to the students in thinking through how science actually works. And students that study economics, they're really interested in, like, okay, the role of the prize as being a motivating factor for the scientist. They think that could be really sensible. Motivation is really important. Other students think, no, it needs to be pure. You shouldn't be chasing prizes. And so in this way, these things can kind of humanize science. Okay, and then the last liberal arts connection is philosophy. And some of these things have already been touched on. But I think when we think about what science is and what science tries to do, it's important to include chemistry as one of the natural sciences, as a part of the activity of natural science. I think a lot of times when philosophers of science have tried to articulate a kind of a logic of discovery for how science works, and even when we think about what is the scientific method in terms of hypothesis testing, chemistry can sometimes be an awkward fit in some of these conversations, and I think it can therefore broaden our conception of what science is. Like I said, with that Woodward synthesis of vitamin B12, what is the hypothesis that's being tested here? What is the particular experiment? It's this big project, but it's a synthetic project. And there's been lots of chemistry is this way, trying to make a new molecule. And so chemistry is about giving us insight into what the world is like, but it's also about creating new things. And that's different. The astronomer doesn't create new things. The astronomer looks out and tries to see what's there. But actually the chemist looks into matter, naturally occurring matter, and then also creates new things. So that's a part of science. And then, of course, leverage down the line in technologies. One reason we might think about the importance of including chemistry when we think about science is that chemistry is an enormous discipline. I think we should think of chemistry as the experimental science per se. Actually, if you look at the number of papers published per year in the different areas of science, by far the biggest is chemistry. Chemistry has more publications per year than the other areas of science, almost as many as the other areas combined. And so it's an incredibly large discipline. And one of the reasons for this is when you make new things, you actually create more open questions than you answer. I think, we think about, like, will we ever get a full picture of exactly what reality is? The so-called theory of everything that physicists might be trying to get at. Well, chemistry doesn't have anything like a theory of everything as its goal, because every time you make a new substance, you've maybe solved a question about how stable that substance is and things like this, but you have opened up any number of questions in terms of characterizing that substance and things like that. So chemistry, in some ways, you could think of it this way: chemistry creates non-knowledge, that is, open questions, faster than it creates knowledge. And so chemistry will never have a comprehensive grasp of reality. It's always creating new questions by creating new substances. And in that way, also, chemistry changes the world. Chemistry, by making something new, it's not just observing the world, it's changing the world in some way. And so the point here is just that chemistry, in terms of some of its methods, is different. It's different than something like a theoretical physics. We talked last night about Newton's law of universal gravitation, and then Einstein's relativity and quantum mechanics. Sometimes I think philosophers of science have really honed in on theoretical physics as being representative of science, and they would do well to remember that chemistry is also part of science. It has quite different aspects to it. And then the final thing with philosophy is, towards the end of this course, I like to have the students think about, like, okay, we've learned all these things about chemistry, including the structure and mechanisms of the molecules that are what make up you, right? In terms of your body, the proteins in your body, DNA, things like that, right? So this raises the question then, wait a second, could a human be understood in terms of chemistry? Like, is a human just a really complicated chemical system? A whole series of molecules and reactions? And so this brings up the idea of reductionism, right? The idea that oftentimes as a scientist, when you have something you want to understand, what you do is you try to understand it in terms of its constituent parts. You try to understand it in terms of something more fundamental. And this is a very powerful mode of analysis, but sometimes I think scientists can mistake this reductionistic impulse as the only way of understanding things, or the best way of understanding things. And that's why they might be prone to talk about humans as if they are these very complex molecular machines. What's going on up here? Lots of very complicated chemistry, right? But I want the students to wrestle with, does that mean that you're nothing more than a very complicated chemical system? And it has implications for the liberal arts, right? Because you could think about, something like psychology. What is it? Well, if you think of it as mostly being, or essentially being, complex biology, you can understand human psychology in terms of the underlying biology. But how do you understand that biology? You understand it in terms of the underlying chemistry. And I'm just talking about chemistry because I'm a chemist. Of course, the physicist will say, well, you can understand chemistry in terms of the underlying physics, and then maybe the mathematician might say, well, physics boils down to mathematics. And these things are all important, but I think it's, each discipline needs to think about what are the features of this discipline that are fundamentally irreducible to the more fundamental discipline. There was a quote by Dirac in the talk last night, a physicist involved with the development of quantum mechanics. He thought that chemistry would ultimately be reducible to physics. These fundamental equations of physics would envelop chemistry. That is, you can understand atoms and molecules in terms of the equations of quantum mechanics. And so it's a provocative claim, and I think it's important for the students to wrestle with, is that the case? Or is there something, or is there a language and a conceptual landscape within chemistry that is irreducible to physics? It's its own unique discipline. And my view is that all of these various disciplines that have their strengths for looking into what is real and trying to capture reality, they have a kind of an autonomy and they have an integrity to them, and they're not reducible to more fundamental things. And this is welcome news to the student of the humanities, because it isn't the case that humanities disciplines are somehow reducible to just the chemical, the neurons firing in the brain and the chemistry of your brain. It has implications for free will versus determinism and things like that. So even something as simple as an introductory chemistry course can get us thinking about, wait a second, what can and what can't just be explained in terms of chemistry, using the concepts and language of chemistry. Okay, now finally, I want to be very clear in acknowledging that And I think this is the case of lots of luckily we had a more practical talk from Mrs. Theory, but a lot of this kind of like connections and historical context and all this stuff. Of course, when it's boots on the ground and you're teaching a course, everyone who's ever taught a course knows that there's this tension between content and context, right? So it's really interesting to be able to go all these different directions, but every teacher has to wrestle with, am I doing that at the expense of the content that are the fundamental ideas that are important for this discipline and important for students to understand? And so that's why I'm not trying to say we should implement all of these things in a high school chemistry course, but rather that in the background they can kind of get us thinking about some interesting connections between something as kind of objective and materialistic as chemistry and all of these other concerns that are a part of the liberal arts. So thank you, and hopefully we have a little time for some questions.
That was Dr. Matthew Young, Dean of Natural Sciences and Professor of Chemistry at Hillsdale College, and his address, The Great Principles of Chemistry, from the Art of Teaching the Sciences in March 2024. To learn more about the Hoogland Center for Teacher Excellence, visit the webpage at k12.hillsdale.edu. Click the Events tab and look for Hoogland Center, or write to cte@hillsdale.edu. I'm Scot Bertram. We invite you to like us on Facebook. Search for Hillsdale College K-12 Classical Education. You also can follow us on Instagram at Hillsdale_K-12. Hillsdale_K-12 on Instagram. Thank you for listening to the Hillsdale College K-12 Classical Education Podcast, part of the Hillsdale College Podcast Network. More episodes at podcast.hillsdale.edu or wherever you find your audio.